Okay, students, so welcome. Let's see. We'll solve few questions based on. First, we'll solve the question based on the laser. You can see on your screen there is a question given. Wavelength of laser source is given, and output power is also given. We need to find the photons emitted in 1 minute when it is in operation. So we have given this data. We'll convert this in all in SI unit. And formula which we use is for n number of photons emitted. Energy of those n number of photons is nh into frequency, which we can convert into the wavelength as c upon lambda. Frequency is equals to c upon lambda. So we know frequency is c upon lambda. Now when we substitute into this formula, the number of photons will comes out to be, when we calculate, is 6 into 10 to 17. Let's move towards the next question. Find the ratio of population of two energy levels in a laser if the transition between them produces light of wavelength 694 nanometer. Temperature is 27 degrees Celsius. So we know Maxwell-Boltzmann condition for finding the ratio of two states. N2 upon N1 is e raised to energy difference between the two states divided by Boltzmann constant into the temperature in Kelvin. Now when we substitute all these values, we'll get this ratio is 8.87 into 10 to minus 31. Similar formula will use. A laser emits pulse of 20 nanoseconds. We'll convert this into time. So 2 into 10 to minus 9 seconds. Power is given kilowatt. So we'll convert in watt. 100 into 10 to 3 watt. We'll use the similar formula and we are able to get the wavelength as 6943 Armstrong. Let's move towards the next question, which is from fiber optics. So we have given numerical aperture 0.2, which is surrounded by air. So if it is air, so we'll take the surrounding refractive index N0 as 1, which is the refractive index of air. Now when we substitute, we'll get the value of N1 as 1.6 and we'll use the formula of acceptance angle sin inverse numerical aperture. Now it is been given that the medium is of refractive index 1.33. So we need to divide it by 1.33 and acceptance angle comes out to be 8.65. Let's move towards the next question. In an optical fiber, the core has a refractive index 1.6, clad has a refractive index 1.3. We need to find the value of critical angle. Now we know the formula for critical angle as IC equals to sin inverse N2 divided by N1. So when we substitute the value, we'll get sin inverse N2 is 1.3 divided by 1.6. So the value comes out to be, so when we calculate, the value for this is 54.34 degrees. So critical angle is 54.34 degree. Now we also need to calculate the value of acceptance angle. So we know the formula for acceptance angle is theta 0 sin inverse of numerical aperture, which is n1 square minus n2 square. So when we substitute, we'll get sin inverse, which comes out to be 60.458 degree. Now let's move to the next question. Calculate the fractional index change for a given optical fiber if the refractive index of core and cladding are this. So fractional refractive index, we know the formula is n1 minus n2 divided by n1. So fractional refractive index, will substitute the value of n1, which is the core refractive index, 1.563 minus 1.498 divided by refractive index of core, which is 1.563. So when we substitute, we'll get the value of fractional refractive index 0.0416. Let's move towards the next question. In an angle of acceptance of fiber is 30 degrees. So we have given angle of acceptance 30 degree when kept in air. Find the angle of acceptance when it is a medium of refractive index 1.33. So we can find the numerical aperture. Theta 0 is sine inverse of numerical aperture when it is surrounded by air. So I can write this numerical aperture is sine inverse or sine of theta 0. Theta 0 is given. So numerical aperture is sine of 30. Sine of 30 is 1 by 2 or zero point 0.5. So numerical aperture is 0.5. Now when it is surrounded by a medium of refractive index 1.33, so I can write the formula. In that case, sine inverse numerical aperture divided by refractive index of surrounding medium, which was earlier case 1, now it is 1.33. So when we substitute the details, sine inverse 0.5 divided by 1.33. So we'll get the value theta 0 as 22.08 degree. 22.08 degree. So let's check this. So 0.5 divided by 1.33 sine inverse of, so we'll get 20.08 degree. 22.08 degree. Let's move towards the next question. So we have given a step index fiber core diameter. So diameter of core is 20 into 10 to minus 6 meter. Refractive index of core is given. Refractive index of core, refractive index of core is given 1.52 and 1 is 1.52 and refractive index of cladding in 2 1.5189. Wavelength is 1.3 micrometer, which I convert in meter. We need to find normalized frequency. So normalized frequency is pi d upon lambda into numerical aperture, which is n1 square minus n2 square. So when we substitute, we'll get this value as 4.052. And the number of modes the fiber support is nm. Maximum number of modes is half v square. So when we substitute half 4.052 square, we'll get the number of maximum modes is 8. Now let's move towards the questions from interference due to thin film. When light falls normally on a soap film of thickness, so we have given thickness 5 into 10 to minus 3 centimeter. Refractive index is given 1.33. We need to find the wavelength in the visible region. So we know wavelength from 4000 to 8000 is in the visible region. Now for this we'll be using the condition of maximum intensity, which is 2 mu t cos r plus lambda by 2 is equals to n lambda. When I lambda by 2 will bring on the right side, I can write this formula as 2 mu t cos r is equals to 2n minus 1 lambda by 2. Now our aim is to find the wavelength. So I can write this wavelength is equals to 4 mu t cos r divided by 2n minus 1. Now it has been said it is light incident normally, so R will be 0. So we'll take R0. When R0, cos 0 will be 1. So for n equals to 1, lambda 1 will be 4 into 1.33 into thickness 5 into 10 to minus 3 centimeter divide by 1. So the value comes out to be 2660 into 10 to minus 8 centimeter. Now for n equals to 2, so it is not in the visible region. Let's check for n equals to 2. 4 into 1.33 into 5 into 10 to minus 3 divide by, at the place of n when I substitute 2, I'll get it just 3. And when we calculate, it comes out to be 8866.67 into 10 to minus 8 centimeter, which is again not in the visible region. Now when I calculate it for n equals to 3, for this the wavelength is 4 into 1.33 into 5 into 10 to minus 3 divide by 5, and when I calculate, this comes out to be 5320 into 10 to minus 8 centimeter, which lies in the visible region. So for n equals to 3, lambda 3 wavelength will lies in the visible region. Let's move to the next question. A parallel beam of light of wavelength incident on a thin glass plate. So we have given wavelength is 5870 Armstrong. Let it be in Armstrong. Refractive index is given 1.5. Angle of refraction R is given 60 degree. Calculate the smallest thickness. So we need to calculate smallest thickness. If the glass plate will appear dark, so for we'll use this condition of minimum intensity. Now we remember the condition 2 mu t cos r plus lambda by 2 is equals to 2n plus 1 lambda by 2. So when I bring lambda by 2 on other side, we'll get 2 mu t cos r is equals to n lambda. Our aim is to find the thickness, so t I can write as n lambda divided by 2 mu cos r. So for minimum thickness, we'll take n equals to 1, and the value of r is given 60 degree. So we'll substitute, and t will be minimum, so t will be thickness will be minimum for the minimum order, which is 1. So minimum thickness will be lambda, which is given 5870 Armstrong divided by 2 into refractive index is given 1.5 into cos of 60 degree. So when we calculate, the thickness comes out to be 3913 Armstrong. Let's move toward the next question. Question number 10. A soap film of refractive index 1.33 is thickness is given and angle of incidence is given. So let's see, first write down the given data. We have given refractive index 1.33. We have given thickness 1.5 into 10 to minus 4 centimeter. Angle of incidence is given 45 degree. Dark band is observed and wavelength is given 5 into 10 to minus 8 centimeter. Order of interference band. So we need to calculate the maximum order n. Since it is dark, so we'll use the condition of 2 mu t cos r plus lambda by 2 is equals to 2n plus 1 lambda by 2. We'll bring lambda by 2 from left side to right side. So we'll be writing this formula as 2 mu t cos r equals to n lambda. Our aim is to find n. So I'll be writing this formula n equals to 2 mu t cos r divided by wavelength lambda. Now we have given mu, but r we don't know. So by using Snell's formula, we'll calculate mu. So mu we know sin I divided by sin r, or this implies r equals to sin inverse sin I divided by mu. So r comes out to be 32.11. Now all these details when we substitute, we'll get n equals to 2 multiplied by 1.33. Thickness is given 1.5 into 10 to minus 4 divided by wavelength, which is given 5 into 10 to minus 8 centimeter. So the n comes out to be 6.75, 6.75, which is maximum order is up to 6. Let's move towards the next question. In Newton's ring experiment, the diameter of fifth dark ring. So what we have given, diameter of fifth dark ring is 0.336 centimeter. The diameter of 15th dark ring 0.59 centimeter. Radius of curvature is given 100 centimeter. We need to calculate the wavelength. Now we know the formula that diameter of any n plus p order minus diameter of fifth order is equals to 4r 15 minus 5 into wavelength. So we can write, now for finding the wavelength, I can rewrite this formula as diameter of 15th dark ring minus diameter of 5th dark ring divided by 4 into r is 100 centimeter into 10. So when we calculate, we take the square of the 15th diameter. So I will be writing this as 0.59 square minus 0.336 square divided by 4 into 1000. Students, when we calculate, we'll get this value of wavelength is 5.88 into 10 to minus 5 centimeter. Let's move towards the next question. Question number 12. In Newton's ring experiment, the 10th dark ring changes from 1.4 to 1.27 when a liquid is introduced between them. Calculate the refractive index of the liquid. So we know the formula for calculating the refractive index of liquid is diameter square when there is a air between the plates, same order diameter when there is a liquid is introduced. 10th dark ring changes from 1.4 to 1.27 when a liquid is introduced. So we'll be writing this as 1.4 square divided by 1.27 square. So the refractive index comes out to be 1.215. Let's move towards the next question. In Newton's ring experiment, the diameter of nth and n plus 8 bright rings are 4.2 millimeter, and so the diameter of nth dark ring is 4.2 millimeter, which we convert in meter. So we'll write this as 4.2 into 10 to minus 3 meter. And diameter of n plus 8 is given 7 millimeter, which I convert in meter will be 7 into 10 to minus 3 meter. Radius of curvature is given 2 meter. So capital R is given 2 meter. We need to calculate the wavelength. So for wavelength, we know the same formula will be using diameter of 8th order dark ring, diameter of nth order dark ring, divide by 4r 4r into p, n plus 8 minus n, which will be 8. So when we substitute, wavelength will be 4.2 into 10 to minus 3 square minus 4.7. So it will be 7 into 10 to minus 3 square minus 4.2 into 10 to minus 3 square divide by 4 into value of r is given 2 into 8. So the wavelength comes out to be 4.9 into 10 to minus 7 meter. Okay, so we are now at the end of, and the last question is, the interference fringes are produced by monochromatic light falls on a wedge-shaped film. Refractive index is given. So wedge-shaped film refractive index given 1.4. Angle of wedge is given theta, 20 seconds of an arc, and the distance between the successive fringes. So we have given fringe weight is 0.25 centimeter, which we convert in meter. So 0.25 into 10 to minus 2 meter. Calculate the wavelength of light. So we need to calculate the wavelength of light before we need to convert seconds into radian. So how to convert the seconds into radian? So theta we need to convert in radian. So first we'll convert in minutes. So it is 20 divided by 3600 multiplied by pi by 180. So when we calculate, we'll get this in radian, 9.69 into 10 to minus 5 radians. Now we know the formula as fringe width beta equals to lambda upon 2 mu theta. So our aim is to find out wavelength. So I'll be writing this wavelength is beta 2 mu theta. So the wavelength will be 2 multiplied by the fringe width is given 0.25 into 10 to minus 2. Refractive index is given 1.4 and we got this value in radian, 9.69 into 10 to minus 5. When we calculate with the help of calculator, we'll get this as 6.783 into 10 to minus 5 centimeter. So with this, we'll come to the end of all the questions of these three chapters. Thank you.